Hello, and welcome back to another CodingBytes speedrun with me, Vince. Today we'll be starting a new series, and we'll actually be speedrunning something that isn't coding. You see, aside from coding or computer science, in the IB diploma course, I have to study 5 other subjects, and one of those happens to be mathematics, where I'm taking Math HL. I thought it would be useful as a reference for me in the future, but also maybe for some other people, if I recorded myself speedrunning the entire Mathematics HL textbook, one chapter at a time. So if you don't know what textbook I'm talking about, I'll put it on the screen here. And if you're taking Math Analysis HL and you don't have it, I highly recommend you get it. It's the best way to learn the course. So today we'll be starting with Unit 1.1, which covers sigma series, sequences, and sigma notation. So let's jump right in. So the first thing we want to ask ourselves is, what is a series? Sorry, what is a sequence? So a sequence is like a list of numbers, say like 1, 2, 3, 4. This is a sequence. And the rules for this is that the numbers have to be written in a defined order following a specific rule. In this case, the series follows the rule n, where n is the current term. And so each of the numbers making up this series is called a term, and all of them have like a number. So for example, the first term of this series is 1, so sequence is 1. The second term of this sequence is 2. The third term of this sequence is 3. The fourth term of this sequence is 4. And therefore the rule is for the nth term of the sequence, the number in the sequence is equal to n. So let's look at maybe a more complex sequence. So if you're aware of the 1, 4, 9, 16, you should know maybe from previous math lessons what this sequence corresponds to. So this is the first term, second term, third term, and fourth term. So in the first term, the number in the sequence is 1. The second term is 4. The third term is 9. And the fourth term is 16. So we know that the rule for the series is that for the nth term, the value is n squared, right? Because 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, and so on. Okay, sequences can also be finite or infinite. So what a sequence being finite means that it starts at a number and stops at a number. For example, this series, or this sequence we have over here, starts at 1 and stops at 16. And if we were to have maybe an infinite series, then let's say this goes on forever, so like, the next term is 25 and 36, it means that it has no end. And so the distinction is made when we put 3 dots after the last term in the sequence. If we do put 3 dots, it means it's an infinite series and it goes on forever. If we don't put 3 dots, it means the series is finite and it stops there. All right. All the terms in a sequence, when added together, are called a series. Sorry, I keep on getting mixed up. They both begin with an S. So when you add all the terms up in a sequence, it is called a series. And like sequences, series can be finite or infinite. So for example, if we add up all these terms in this finite series, notice there's no ellipsis over here, we get 1 plus 4 plus 9 plus 16, which is equal to 30. And so this is a finite series, which value is 30. If we put an ellipsis instead, this would be an infinite sequence and would also be an infinite series, as it does not converge. So finally, we have to talk about sigma notation. And sigma notation can be used to express a series in a compact form, which makes use of the general term written in terms of a variable r. So what sigma notation is, it looks something like this. And this is the sigma symbol. At the bottom, we define a starting point. Say r is equal to 1. And at the top, we define a stop point, 10. If you watch some of my coding speedruns, you might notice this looks a bit like a for loop, and I do think of it sort of as a for loop as well. So for example, if our series is just like the number itself, then what this would evaluate to is 1 plus 2 plus 3 plus 4 until 10, which we know is equal to 55. Right. Say we want to have maybe a more complex series, say r squared, then this would be the sum of 1 plus 4 plus 9 until 100. And unfortunately, I don't know that off the top of my head, but the value of this would be equal to that. So that's all we need to know to start solving the problems in this chapter, and we find those under exercise 1A. So the first question is, so I'll write the question up here. So for each, oh, it's gone. For each of the following sequences, write the next 3 terms and find the general term. So the general term is the rule linking all of the terms in the sequence with each other. So the first sequence we're given is 3, 4 point, so it's a bit neater, I'll write it in this text. So first we have 3, 4.5, 6, 7.5, and it continues infinitely. So how do we find the next 3 terms? Well, if we notice here, to get the next term, we're simply adding 1.5 to the previous term. So, for example, from 4.5 to 6, that's a difference of 1.5. From 6 to 7.5, that's a difference from 1.5. So the next 3 terms would be, well, 7.5 plus 1.5, which is equal to 9. And then 9 plus 1.5, which is equal to 11.5. No, 10.5. What am I doing? Sorry. 10.5. And then the next term is 10.5 plus 1.5, which is equal to 12. So these are our next 3 terms, and now we need to find the general term. So we know that the first term was 3, the second term is 4, and then like for every term after that, we add 1.5. So what will be the general term? Well, we know that it has to be some sort of 1.5n, because for every increase, like for every next term, we add 1.5 to the value, and we know it starts at 3. So when n equals 1, so this value would be we have to actually add a constant. So to make the first term equal to 3. So when n is 1, we have 3 is equal to 1.5 times 1 plus c. And therefore, we know c is equal to 1.5. And so we have our general term, un is equal to 1.5n plus 1.5. Un is a value we use to denote the current value in the sequence. Actually, we should be using r. The letter you use does not matter too much, but r usually stands for a positive number, and in this case, we're normally dealing with sequences with the terms starting at 1. Okay, so that's how you solve that first question. I think I will be doing 2 questions from each sub-question, because after that the pattern gets pretty repetitive, and I would highly encourage you to try them on your own. 11(8). Okay, so here we see a descending series, which each term being the previous term minus 3. And so what would the next 3 terms be? Well, what's 8 minus 3? Well, that's 5. 5 minus 3? Well, that's 2. And 2 minus 3 is equal to negative 1. So these would be the next 3 terms in the series. To find the general term, we know that the general term will be equal to some sort of negative 3r plus a constant to make the first term 17. So let's find out what the constant is. We know 17 is equal to negative 3 times 1, because it's the first term, plus c. And so we know c must equal 20 if we add 3 to both sides. To remove this, and so 17 plus 3 is equal to 20. So our general term must be ur is equal to negative 3r plus 20. And that is our general term. Okay, now let's move on to the next question. If you're still unfamiliar with what a sequence is, I would suggest you try and solve sub-questions C, D, and E, but I will be moving on. So the next question is write down the first 5 terms of each of the following sequences. So our sequences, the first sequence we have is UR is equal to 3 minus 2R. Okay, so to find the first term, we simply put R is equal to 1. So the first term, or U1 as we call it, is equal to 3 minus 2 times 1, which is equal to 1. So the second term is equal to 3 minus 2 times 2, which is equal to negative 1. The third term is equal to 3 minus 2 times 3, which is equal to negative 3. The fourth term is equal to 3 minus 2 times 4, which is equal to negative 5. And finally, the fifth term is equal to 3 minus 2 times 5, which is equal to negative 7. So these are the first 5 terms of this sequence. Okay, let's move on to the next sequence. So the next sequence is r divided by 2r plus 1. Okay, so for our first term is equal to 1 divided by 2 times 1 plus 1, which is equal to 1 divided by 2 times 1 is 2 plus 1 is 3, so our first term is 1/3. So our second term is equal to 2 divided by 2 times 2 plus 1, which is equal to 2 over 2 times 2 is 4 plus 1 is 5, so 2 over 5. Oh. So for our third term, this is equal to 3 divided by 2 times 3 plus 1, which is equal to 3 divided by 7. Our fourth term is equal to 4 divided by 2 times 4 plus 1, which is equal to 4 divided by 9, and I hope you can start to see the pattern. And our fifth term in the sequence is 5 divided by 2 times 5 plus 1, which is equal to 5 over 11. So these 5 terms, scroll up, these 5 terms are the first 5 terms of the series. Let me just, yeah, that's it. Okay, let's move on to the next question, which is, let me just erase all of this. Okay. So the next question is, write each of the following sequences using the general term. And our first sequence is 5, 10, 15, and 20. Huh, how nice. So we know the difference between each term is 5 each time, and, well, that means our sequence will compose of UR is equal to 5R plus, actually it's just 5R, because if you notice, for the first term, it's equal to 5 times 1, which is already equal to 5, and this is already the first term, so that's how you write it. Now let's try a more challenging question, so I'm going to skip all the way to D for this question, because I think it's important to show you how to write the nth term for something that's not a linear sequence. So we have 1, negative 1/3, 1/9, negative 1 over 27. So I hope you can see the pattern here. And the pattern is that each next term is the previous term multiplied by negative 1/3. See, so 1 times negative 1/3 is negative 1/3, negative 1/3 is 9, 1/9 times negative 1 over 27, sorry, times negative 1/3 is negative 1 over 27. So for our general term, this would be, look, something like negative 1/3 to the power of r minus 1. And if you have done geometric series before, you might recognize this pattern, but if you haven't, let's see why. So what happens in our first term? So for our first term, when r is 0, we have negative 1/3 to the power of 1 minus 1, which is equal to 0. And anything to the power of 0, remember, is 1. So for our second term, we have negative 1/3 to the power of 2 minus 1, which is equal to 1. And this would equal negative 1/3, and so on. So that's how you find the nth term for that question. Let's go to the next problem. And if I'm going too fast, let me know if I should speed up, and if I'm going too slow, let me know if I should, if I'm going too fast, let me know if I should slow down, and if I'm going too slow, let me know that I should speed up in the comments. So finally, we get to some sigma notation, and the question is, write each of the following series in full. And, well, I'll write down the series here. So we have r starts at 1 and it ends at 4. And the pattern is 2r times 1 minus r. Okay. So what we get is we start at 1. So our first term is 2 times 1 times 1 minus 1, which is equal to 0, because 1 minus 1 is equal to 0. Now our second term is 2 times 2 times 2 minus 1, which is equal to 4. Our third term is equal to 2 times 3 times 3 minus 1, which is equal to 6 times 2, 12. And our fourth term is 2 times 4 times 4 minus 1, which is equal to 8 times 3, or 24. So our final series is equal to 0 plus 4 plus 12 plus 24. Have I made a mistake? 2, 4, 8, 3, 12, 2, 3, 6. Yeah, that's fine. 4. Okay, I think this is correct. And so the final series is equal to 4 plus 12 plus 24, which is 40. Nice. So let's move on to the next question. So the next question is, let's skip to a harder question. So now I think I've decided I will do the first and the final questions, sub-questions in each question, because doing the rest might take too long, and after all, this is a speed run. So if r is between 0 and 3, and our sequence is r squared, not r cubed, r squared minus 3, then the 0th term is equal to, what am I doing? 0th term is equal to 0 squared minus 3, which is equal to negative 3. The first term is equal to 1 squared, oh, why does that change color? Minus 3, which is equal to negative 2. The second term is equal to 2 squared minus 3, which is equal to 1. And finally, the third term, 3 squared minus 3, is equal to 6. So to get the series, we add all of these terms together. So this will be equal to negative 3 minus 2 plus 1 plus 6, which is equal to negative 5 plus 7, or is equal to 2. So the final series is equal to 2. Okay, sounds good. So moving on to the next question. We want to, for each of the following series written in sigma notation, write the first 5 terms. Okay. So let's see what the first series is. So it ends at infinity, begins at 1, and it's equal to r plus 1 over r squared. So the first 5 terms will be 1, 2, 3, 4, and 5. So the first term is 1 plus 1 over 1 squared, which is equal to 2. The second term will be 1 plus 2, sorry, other way around, 2 plus 1 divided by 2 squared equal to 3/4. The third term will be 3 plus 1 divided by 3 squared is equal to 4/9. The fourth term is 4 plus 1 divided by 4 squared, which is equal to 5/16. And the fifth term, 5 plus 1 divided by 5 squared, which is equal to 6/25. So let's go back to the top. And the first 5 terms of this series will be 2 plus 3/4 plus 4/9 plus 5/16 plus 6/25. So this will be our answer. Now note this is an infinite series, so we can't say, like, okay, actually we should put the 3 ellipses after this last term. So because we, this, at least for now, we don't know how to calculate the sum of this infinite series since it goes on forever. Or does it? We'll see about that in the next speedrun, but that's a topic for a later date. Oh, come on, and erase this. Okay, so our next series is starting at infinity, and sorry, ending at infinity. What am I doing? Starting at 1, r to the power of r. Oh dear. So well, you have to write the first 5 terms. So the first term is 1 to the power of 1, which is equal to 1. Second term is 2 to the power of 2 is equal to 4. I mean, still pretty easy. Oops. Third term is equal to, as soon as I erase this, 3 to the power of 3 is equal to 27. Fourth term is 4 to the power of 4 is equal to 256. And finally, the fifth term, which is 5 to the power of 5, which is 3,225, if I'm not mistaken. 5 to the power of 5, yep, sorry, 3,125. Oops. 3, that's a 1, 3,125. So, if we go up here, and we now want to have the first 5 terms, plus, because it's a series. 1 plus 4 plus 27 plus 256 plus 3,125. And that will be our final answer. Okay, moving on to the last question of the day. So the last question is, write each of the following series in sigma notation. Okay, so let's look. Our first series is, our first series is 8 plus 5 plus 2 minus 1 minus 4. And how you think about these series is you want to think of them as each term is part of a sequence. So what's the difference between these terms? It's 3. The difference between these terms is 3. It's clearly a linear sequence. So what we would do then is we need to find the general term of the sequence, which in this case is equal to 3r, negative 3r actually, sorry, because we're going down. And the first term is 8, so 8 is equal to negative 3 times 1 plus c, so c is equal to 11. C is equal to 11. And so we have our series negative 3r plus 11. And now we can transform this into sigma notation. Since we're only given the first 5 terms of the series and it's clearly not infinite, we can just define a series that starts at the first term and ends at the 5th term. So we want to end at 5, start at 1, and we simply substitute this sequence here, negative 3r plus 11. And that's it. This is the answer to that question. So, moving on to the real final question of the day. Our last series that we want to get the sigma notation of is 3k plus 6k plus 9k plus 12k plus 15k. Right. And, well, what's the series here? Each term is increasing by 3k, and so we're going to be using two variables in the sigma notation. Clearly it starts at 3k, so our sequence ur is equal to 3kr. Finally, since we only have 5 terms, the sigma notation is simply ending at 5, starting at 1, 3kr. And that's it. So that's the end of chapter 1.1. I hope that you now know a lot more about series, sequences, and sigma notation. If you like the speed run, or if you didn't like it, leave a comment down below. And if you did like it, maybe leave a like as well, and make sure to subscribe for more speedruns. See you next time.